A neutron star with a pulse. A pulsar flashing across the cosmos. We're used to celestial objects showing rhythmic behavior. But an interstellar comet? That's new territory. Welcome to Infinite Voyage news and updates. Tonight we're covering one of the latest discoveries about 3I Atlas, a precise 16-hour pulsing pattern that's been confirmed through peer-reviewed research. We will break down what's causing this rhythm, why it's not what scientists initially thought, and what it reveals about the nature of this object. Let's get into it. Between July 2nd and 29th, an international team led by planetary scientist Santana-Ros conducted systematic photometric observations using multiple ground-based telescopes, the Falks telescopes, Nordic Optical Telescope, and South Africa's SALT facility. Their findings, published in Astronomy and Astrophysics, confirmed something unusual. 3I Atlas exhibits a clear periodicity of 16.16 hours, plus or minus 0.01 hours. The light curve showed a peak-to-peak amplitude of approximately 0.3 magnitudes, brightness variations of tens of percent, repeating like clockwork every 16 hours. First assumption? Rotation. Maybe 3I Atlas is an elongated nucleus tumbling through space. When the long axis faces us, we see more reflected sunlight. When it rotates edge-on, brightness drops. Simple geometry. But that explanation doesn't work. And here's why. Hubble Space Telescope observations taken on July 21st revealed something critical. Most of the light we're seeing doesn't come from the solid nucleus at all. It comes from the glowing coma, the cloud of gas and dust surrounding it. The nucleus itself is tiny, with an estimated radius of only 2 to 3 kilometers. The research team calculated that the nucleus reflects less than 1% of the total light at 1 micrometer wavelength. Less than 1%. The remaining 99+% comes from the coma particles scattering sunlight. So if the nucleus is that small and contributes so little to overall brightness, its rotation alone cannot explain 30% brightness variations. The light curve amplitude would require an axis ratio of about 0.76 to 0.83, meaning a significantly elongated shape. But even if the nucleus were that elongated, it's simply too small and too dim to modulate total brightness by that much. The coma dominates everything. So what's causing the heartbeat? Jets. Collimated streams of gas and dust erupting from the nucleus. Multiple images throughout July and August showed 3I Atlas ejecting material in narrow concentrated jets. Sometimes as many as 7 or 8 distinct outflows visible in a single image. These aren't diffuse clouds. They're directed streams shooting outward into space. If these jets turn on and off periodically, the surrounding coma brightens and dims in response. More material ejected means more particles scattering sunlight. Less material means dimmer coma. The 16.16-hour period isn't telling us about the shape of the nucleus. It's telling us about the behavior of the jets. Harvard astrophysicist Professor AviLoeb described it this way. This resembles a heartbeat, with a puff of gas and dust serving the role of a stream of blood through the coma periodically over the rotation period. The mechanism, if 3I Atlas is a natural comet, works like this. Imagine a large pocket of exposed ice on one side of the nucleus. As the nucleus rotates, that ice patch faces the sun, heats up, and suddenly sublimates, erupting outward as gas and dust. Then the nucleus continues rotating. The ice patch moves into shadow, and the eruption stops. 16 hours later, the same patch faces the sun again, and the cycle repeats. Assuming an outflow velocity of about 440 meters per second, consistent with Webb telescope observations, the sublimated material could travel roughly 25,600 kilometers outward during one full rotation cycle. Now, why would ice only be exposed on one side? Over millions of years traveling through interstellar space and previous stellar encounters, the surface gets baked. Solar radiation cooks the outer layers, creating a dark, dusty crust that insulates the ice beneath. Most of the surface does nothing when heated. The crust is too thick. But in certain areas, a crack, a pit, a cliff face, fresh ice reaches the surface. Only that exposed patch reacts to sunlight. When that active site faces the sun, it erupts. When it rotates away, it goes quiet. This is common cometary behavior. Real comets don't outgas uniformly. They erupt from specific weak spots. The Santana-Ros study measured dust activity levels at approximately 300 centimeters AFR, comparable to distant Jupiter family comets. Dust mass loss rates were estimated between 0.3 and 4.2 kilograms per second. That's relatively modest, but consistent with distant, weakly active comets at similar heliocentric distances. Spectroscopic observations revealed progressive reddening in the visible spectrum. The spectral gradient increased from about 17% per micrometer on July 4th to nearly 23% per micrometer by July 25th. That reddening suggests increasing dust activity as the comet warmed up. Beyond 0.7 micrometers, the spectrum flattened, and in the near infrared, it showed slight bluing, consistent with changing particle size distributions, potentially indicating larger grains dominating the dust population. All of this points to natural cometary behavior. The morphology, the colors, the dust production rates, they fit within the range we see for outer solar system comets. But here's where Professor AviLoeb raises an important methodological point. If 3I Atlas were a technological object, an artificial spacecraft, the jets wouldn't need to point toward the sun at all. They could fire in any direction. Natural jets driven by solar heating always orient sunward. Artificial thrusters could point anywhere. Loeb suggests a definitive test. Create a time-lapse movie over several days and watch where the jets brighten. If they brighten in a sun-facing pattern, it's natural sublimation. If they brighten in directions unrelated to the sun's position, that would be a significant indicator of technological origin. That test hasn't been done systematically yet. To be clear, the overwhelming scientific consensus based on current data is that 3I Atlas is a natural comet. Radio observations from Meerkat detected hydroxyl radicals on October 24th, molecules created when water breaks down under sunlight. That's exactly what you'd expect from a comet losing water. Spectroscopic data shows compositions similar to solar system comets. But Loeb's point is valid from a scientific methodology standpoint. We should test the hypothesis properly. Science advances by ruling things out with data, not assumptions. 3I Atlas survived perihelion on October 29th intact. Recent images showed jets continuing to erupt, meaning the nucleus didn't fragment. And now comes the critical window. On December 19th, 2025, just days from now, 3I Atlas makes its closest approach to Earth. That's our best opportunity for detailed observation and data collection before it recedes into interstellar space forever. Hundreds of ground-based observatories are tracking it. Hubble and Webb have allocated observation time. In the coming weeks, we're expecting high-resolution data, spectroscopy, photometry, imaging, polarimetry. that will reveal particle size distribution, chemical composition, outgassing rates, and detailed jet morphology. Depending on what that data shows, we'll have a much clearer picture of our third interstellar visitor ever captured by our modern astronomic instruments. If the jet's speed, composition, and mass loss match expectations for sublimating ice, the natural comet interpretation will be strongly confirmed. If the jets move at velocities orders of magnitude higher than sublimation can produce, or if their directionality doesn't correlate with solar heating, then we'd have genuine anomalies requiring deeper investigation. Right now, the 16.16-hour heartbeat is telling us something fundamental. This object's brightness variations are driven not by its shape, but by its activity. The jets are the story, and those jets are firing in rhythm, pulsing outward every 16 hours like a cosmic metronome. Whether that rhythm is driven by solar heating and rotation, or by something else entirely, we'll know soon. December 19th is the moment of truth. This is what makes interstellar objects valuable. Every one we detect is a physical sample from another star system, teaching us about volatile chemistry and dynamical evolution happening light years away. When Vera Rubin Observatory comes fully online, we expect to detect dozens of these objects. Each one will refine our understanding of what's normal, what's unusual, and what's genuinely anomalous. For now, 3i Atlas continues inward, its jets pulsing every 16 hours, a heartbeat from interstellar space. We'll be watching closely during the closest approach, and you can be sure we'll bring you the results as soon as the data drops. That's the latest on 3i Atlas. Keep looking up. There's always something incredible happening out there. Thank you for watching until the end, and I look forward to reading your comments about these heartbeat-like pulses. I'll see you in the next Interstellar Scientific Update.